In this video, we're going to wrap up chapter 29 by talking about the Gauss's law in magnetism. So suppose we have a, so this is a surface right here, and we have the magnetic field vector, and if this is the direction of the area vector, then if there is some angle theta between my magnetic field vector and my area vector, then I can define the magnetic flux. It's given by this equation right here. It's just the dot product of B times the A, and this integral is done over the entire surface. So we notice that if the magnetic field is uniform and not changing, then this is just going to reduce to the dot product of B and A of the B vector and the area vector, which is given by this quantity right here. It's just the magnitude of the magnetic field times the area times the cosine of the angle between the magnetic field vector and the area vector. So let's kind of illustrate how the definition of the magnetic flux. So on this very first picture, we notice that so if we have a surface, so this surface is on the xy plane. So if my surface is on the xy plane, then the area vector is pointing in the z direction. And so if I have a magnetic field that is pointing in the x direction here, then notice that the magnetic field is going to make 90 degrees with respect to the area vector. So in this example, when you calculate the flux is just going to give you 0, because the magnetic field is perpendicular to the direction of the area vector. Now on the second picture here, the magnetic field is actually parallel to the direction of the area vector. So you can see that the B vector and the area vector are pointing in the same direction. So that would give you the maximum value of the flux. So in the first example here, the flux is 0. Here the flux is just going to be the maximum value because the magnetic field is parallel to the area vector. Now the magnetic flux is calculated in these units right here. Is in units called the Weber. So 1 Weber is just given by 1 Tesla meter square. So it's a magnetic field of 1 Tesla in a surface that has an area of 1 meter square. So 1 Tesla times 1 meter square gives me a magnetic flux of 1 Weber. All right. So now let's look at this example right here. So this is example number 29.7. So in this example, we're going to calculate the magnetic flux through a rectangular loop. So suppose that we have a rectangular loop of width A and length B, and it's located near a long wire that carries a current I. And then it also tells us that the distance between the wire and the closest side of the loop is C, and then it says that the wire is parallel to the long side of the loop. So find the total magnetic flux through the loop due to the current in the wire. So this is the setup of my problem right here. So we have so this is my conductor, this is my wire that carries the current I. Now we notice that the current, so the magnetic field produced by this wire is not a uniform magnetic field, but it's a magnetic field that would depend on the distance from the wire. So as you go further away from the wire, the strength of the magnetic field is going to reduce. So it means that in this type of problem here, so because the magnetic field is non-uniform, I need to use calculus to calculate the total magnetic flux that is going to go through through this surface right here. All right. So when I set up my integral here, I can say that the magnetic flux is just the integral of B times dA. So again, notice that because the magnetic field is going into the paper and the area vector is also going into the paper, it means that the magnetic field vector is always going to be parallel to the area vector. So when you take the dot product, you just get B times dA because the angle is 0, so cosine of 0 is equals to 1. So we end up with this equation right here. So the magnetic flux is just given by mu naught times I over 2 pi radius. So notice that the mu naught I over 2 pi radius is just the magnitude of the magnetic field of an infinite wire that carries a current I. Now using calculus, I know that my dA, so dA is the area of this rectangular region that you see right here. So this region here, so this has a small thickness of dr and the length of b. So it means that the area of this rectangular strip right here is just b times dr. So when I do this, I can rewrite this as mu naught I over 2 pi, and then I want to run this integral from so when I do this integral, I want to integrate from r equals to this point here, so from r equals to c to r equals to a plus c. So the distance from here to here is c, the distance from this point to this point is a plus c. So if you substitute that, you run this integral, since the integral of 1 over r is just the natural log, you end up with this final equation right here. So this is a magnetic flux that goes through this surface right here. So again, notice that this is an example where the magnetic field is not just a uniform magnetic field, so it means that we need to calculate the magnetic flux by doing an integral. All right, so generally so Gauss's law in magnetism simply says that the net magnetic flux through any closed surface is always equals to 0. So this makes perfect sense because if we look at the closed surface, so for example, if you look at this dotted line right here, so you can see that if this is a surface here, then if I'm looking at the bottom here, so I have magnetic field lines going into the surface and magnetic field lines going out of the surface. So when I calculate the flux at the bottom, I know that the area vector is always pointing out, and then at the top here, the area vector is also pointing out. So again, if you sum all the contributions, you're going to notice that the net magnetic flux is just going to be equal to 0. And this is very special because if you remember, we said that the flux of the electric field in a region that contains a charge is proportional to the charge. So in magnetic field, because there is no charges, the net magnetic flux that goes through any closed surface is just equal to 0. So we're going to be using this concept later on. So once we get into chapter number 30, we'll talk a little bit about using this concept. But again, what we're saying is that Gauss's law in magnetism simply says that the net magnetic flux through any closed surface is always equals to 0.